Yay!
Yay! Hey everyone, here's another example of work and kinetic energy that we can do. This one involves friction, which you might see sometimes. Suppose we have a box sliding across a rough floor, and it starts off at 10 meters per second. It's a 10 kilogram box, mu is 0.4. And what you might want to know is how far will the box slide? Okay, and what do we know? What's our fundamental, for this unit, what's our fundamental relationship is that the work done in a system is just going to be equal to the change in kinetic energy, right? So this is going to be K final minus K initial. Okay, well, the box starts off with a VI, right? So the box starts off with a kinetic energy, so there's a KI. But look, how far will the box slide? What does it mean? That means it's going to come to a stop. We want to know how far it goes before it comes to a stop. And if it comes to a stop, then the final kinetic energy is going to be zero, right? The V final, is going to be zero. Neat. So the work done is going to be minus the initial kinetic energy. You might worry about that minus sign, minus the initial kinetic energy, but we'll see. We'll see what happens to it. Okay, what work is being done? Right? If the work is being done, there's got to be a force. What force are we talking about? Well, as it slides across the floor to the right, there's no force pushing it to the right, right? It just starts off going 10 meters per second. So the only force, the only horizontal force, right, that's affecting the speed is the frictional force. That's it. And what direction is friction going? It's going that way. Right? It's opposing the motion of this thing. So it's the frictional force that's supplying the work. So the work done by friction, here's what I'm saying, the work done by friction is got to be equal to minus the original kinetic energy. Here's what's going to happen. It must then be true, right, that the work done by friction is less than zero. Frictional work is going to be negative, because what it's going to do is it's going to take energy out of the system. When you compute frictional work, you're usually going to get a negative answer because you're taking energy away. And you have to think about it carefully. I mean, what does it mean to take energy away? Because if you say, oh, you lose the energy, then you're going to be mad because people have been telling you all during this unit that you can't gain or lose energy. It's conserved, right? But all we mean is, if friction takes away the energy, it sort of takes it out of the system we're interested in. Because what really happens, I mean, if you rub your hands together or you slide across the carpet, you know immediately what happens, and that is that the box gets warm and the ground gets warm. And what does it mean for things to get warm? It just means that their atoms and molecules are jiggling, they have motion. So all you've really done is transferred the motion from the box into the motion of, uncountable trillions of little particles. And if you add them all up, the kinetic energy of that little jiggling of the particles because things are getting warmer, then energy is conserved. Okay, but for our purposes, if the energy leaves the system like that due to friction, usually we just call it lost energy, or non-conservative forces is another thing you'll see in the book. And all that means is you can't account for all the energy, right? If energy is conserved, then you can account for it all, beginning equals end. If it's not conserved, if there are non-conservative forces, that means you end up with a discrepancy. Sort of like your bank account not balancing, right? Some money went away. Some energy left the system. So did it really leave the system? No, you can account for it if you're careful. But we don't care about that, right? All we care about is from the system of the box sliding on the floor, the energy is gone. We start off with some initial kinetic energy and we wind up with zero. But we can account for it by the work done by friction. And what's the work done by friction? It's just going to be, let's see. It's the force of friction times the distance that it slides, right? But again, we need to be careful. Let's be careful. Because the force of friction is to the left, and the direction that we're sliding is to the right, right? These are actually, like we did last time, those are actually kind of vectors, aren't they? So F dot D, this is equal to, this is minus KI, but this is F D cosine theta where that's the angle between the two vectors. If the box is traveling that way, what's the angle between those two vectors? It's 180 degrees. And the cosine of 180 degrees is -1. So there's where our other negative sign is going to come in. So this is going to be minus FD is minus KI. So those minus signs are going to go away. What is the frictional force? We already know the magnitude of it by now. It's just mu times N times D. And the initial kinetic energy is 1/2 mv squared. All right. So we're just about ready to go, right? So let's see. This is going to be, what is the initial energy? 1/2 m. M is 10. V is 10. So it looks like that's going to be 500 joules is the energy we start off with. And we're looking for D, right? So D is going to be this 500 joules divided by 0.4 times the weight. What is the weight? Mg. And the normal force is just going to be mg in this case. So that's 100. So that's 500 divided by 40, or 12.5 meters, right? We start off with 500 joules of kinetic energy, and then all that energy is used up by friction. And so we just need to find out how long will you go, what distance will you go until friction uses up 500 joules of energy. And it turns out it's 12.5 meters. Very cool. So this concept of using up available energy that you start with is a really powerful one. I mean, just to illustrate, could we solve this another way? Sure, you could. Let's do it real quick. Kinematics. Bandwidth is cheap, right? Whoops. Not so cheap, I can keep making spelling mistakes. Kinematics. Can we solve it the old way using kinematics? Yeah, we can, because we know that V final, how about this one? V final squared is V initial squared plus 2A delta X. Remember that one? Where now V final squared is going to be 0, right? I know my V initial, and I want to find out that delta X. So delta X, let's see, that's going to be minus VI squared over 2A. So it's going to be minus, I'm squaring VI and then taking the minus, right? So it doesn't necessarily go away. So this is going to be minus 100 over 2 times A. What's the acceleration? Well, it's slowing down, right? Really, it's a deceleration. And so this is going to be, I suppose we should do it over here. A, what is that? It's the frictional force divided by the mass. The frictional force is just going to be mu times N. So it's going to be 40 divided by 10, or 4 meters per second squared, right? Going back to our early term kind of way of doing things. But it's a deceleration. We're slowing down, so it's going to be a minus 4. And so again, the minus signs go away. And again, if you do this, you're going to get 12.5 meters, right? This checks out. So sure enough, you'll get the same answer if you do it 2 different ways. But the point is that using energy conceptually is a much cooler framework, right? It's easier to get your head around instead of just symbols and velocities and accelerations in kinematic formulas. Now we have sort of a model for gaining and losing energy that just conceptually is a lot easier to solve problems with. And as we're going to see, it's going to be far more powerful. So can you solve some of these problems the old way? Sure. And I'd encourage you to, just to make sure that you get the same answer going 2 different directions, or two different ways to do it. But what we're suggesting in this chapter, in this unit, is that energy is just a way more powerful conceptual framework in which to solve problems. That you can do things for which you cannot do kinematic formulas, as we'll see coming up.